Our next elementary potential flow element is a point source, and that looks like some point in space with flow emanating out in all directions. Now I can really only draw this in 2D, but this is a three-dimensional point source, and so flow is emanating out in all three dimensions evenly. And the way we write that is the velocity potential phi as a function of r theta, and we'll write this in cylindrical coordinates, is equal to minus q over 4 pi r, where q is the source strength, and it's also the volume flow rate. Okay, so then we can get the velocity at any point in that flow field. It's equal to the gradient of phi, which equals, if you just take the derivative of phi in cylindrical coordinates, we get q over 4 pi r squared in the r hat direction, and then 0 in the theta direction, and 0 in the phi direction. Now notice that the point source also has a singularity at r equals 0. We'll just write that down. Singularity at r equals 0. That's right at the center here, where this does not satisfy Laplace's equation, but at every other point in the flow it does satisfy Laplace's equation. And you can see that the velocity drops off as 1 over r squared, and that's to keep the volume flow rate constant throughout the flow field. One last thing to note is that if q is negative, this becomes what's called a point sink instead of a point source. That just simply means that the flow is emanating towards the point, or kind of being swallowed by that point, instead of emanating from that point.